Take a look at this function, e to the power s over log x. It looks like a typo. It behaves like a riddle. For x between 0 and 1, it glides down from 1 to 0. And near x equals 1, it is infinitely flat. Every single derivative vanishes there, just like the famous smooth bump function. But the real secret appears when you change coordinates. If y equals e to the s over log x, then log x times log y equals s. Exactly. In log coordinates, this function is a hyperbola. Hold that thought. It's the first of 3 hyperbolas hiding in this formula. The curve encloses a finite area, so we can normalize it into a probability density on the unit interval. The normalizing constant looks hopeless until you substitute t equals minus log x. The unit interval unrolls onto the positive half line, and the density becomes e to the minus t minus s over t. That integral is a classic. It equals 2 root s times k1 of 2 root s, where k1 is a modified Bessel function of the second kind. So our innocent function is secretly a Bessel factory. In t-space, the density is a clean bump, and its peak sits exactly at the square root of s. Crank up s, and the bump marches to the right, dragging the original samples toward 0. Now for the structural reveal. Write the density as the exponential of s times a statistic minus a log partition function. That is the signature of an exponential family. The sufficient statistic is 1 over log x. The natural parameter is s, and a of s is the log of our Bessel expression. Let's zoom out. In t-coordinates, density is proportional to t to the lambda minus 1 times e to the minus a t minus b over t, form the generalized inverse Gaussian family. 3 parameters, one of the great workhorses of statistics. Our family is a one-dimensional thread inside it. Lambda equals 1, a equals 1, and b equals s. One quirk, s cannot go negative, or the integral explodes. So the parameter space is a ray, and sitting right on its edge at s equals 0 is the uniform distribution. Pair is what geometry enters. Picture every probability distribution as a point, and call 2 points close when their distributions are hard to tell apart from data. The natural roller is Fisher information. It measures how fast the density changes when you wiggle the parameter. For an exponential family, it is simply the variance of the sufficient statistic. Here, the variance of 1 over log x. Near the uniform edge, that variance blows up like 1 over s. Sounds fatal, but distance is the integral of the square root, and 1 over root s is integrable. So the uniform distribution sits at a finite Fisher row distance, about 2 root s close in. The far end is different. Lengths keep accumulating forever as s grows. Our family is a ray with 1 reachable shoreline and 1 infinite horizon. To see genuine curvature, we need a second dimension. So let the other exponent breathe. Tilt the density by x to the a minus 1, equivalently, e to the minus a t minus s over t. Now we have a 2-parameter statistical manifold, a half-plane of distributions. And it has a hidden symmetry. Raise your samples to a power, and you stay inside the family. A becomes over c, and s becomes s times c. Relabeling data creates no information and destroys none, so this move is an isometry of the Fisher metric. Its orbits are the curves where times s stays constant. Hyperbolus, that is number 2. Because of the symmetry, all the geometry depends on a single invariant, omega equals 2 root as. We computed the Gaussian curvature across the entire manifold, and it is negative everywhere. Steeply negative near the boundary, then climbing and leveling off at exactly minus 1/2 as omega grows. Minus 1/2 is a famous number. It is the curvature of the Gaussian family, whose Fisher geometry is precisely a hyperbolic plane. Negative curvature is the hyperbolic signature. Geodesics that start out parallel drift apart, and triangles come out thinner than their flat cousins. But information geometry has two different notions of straight. Straight lines in natural parameters are called geodesics. They interpolate between distributions exponentially. Our original family lies on the vertical line, a equals 1, perfectly straight, a genuine geodesic of the big manifold. The Fisher ruler disagrees. We computed the shortest path between two members of the family, and it bows sideways off the line, borrowing some tilt to save length. One family, two geometries, straight for exponential mixing, curved for the metric. So why do people care about this corner of the distribution zoo? Because the generalized inverse Gaussian is everywhere. In finance, mix Gaussians whose variance is GIG distributed, and you get the generalized hyperbolic family whose log density is, literally, a hyperbola. That is number 3. Barndorf-Nielsen built these to model wind-blown sand. Today, they model the heavy tails of asset returns. In Bayesian statistics, GIG is a conjugate workhorse. In sparse regression samplers, like the Bayesian lasso, the local variance parameters have GIG posteriors. And the inverse Gaussian member of the family is the exact law of when a drifting Gaussian motion first hits a barrier, the hitting time distribution of finance and neuroscience alike. One last resonance. The Bessel function that normalizes our family leads a double life. On the hyperbolic plane, K-Bessel functions are the building blocks of the Fourier expansions of Eisenstein series, and the constant term of those series carries the completed Riemann zeta function. One strange little formula. A hyperbola in log-log space. An exponential family threading the generalized inverse Gaussian. A negatively curved statistical manifold with hyperbolic symmetry. And a Bessel heartbeat that echoes all the way to zeta. Not bad for a function that looks like a typo.